Our next presenter, Stuart, McMurray, and Carson Cease. Thank you.
You're welcome. And thank you for coming to our talk. So anyways, hi, I'm Stuart McMurray. We'll talk about a bit of programming in Go. So background for me real quick. I'm Stuart. I'm a red teamer at IronNet. It's a Twitter QR code. Really what you want to do when a hacker puts a QR code in front of you is take a picture of it. Red teamer at IronNet. I'm on the Unix side of things mostly, and more and more on the Windows side, or excuse me, on the networking side of things, as my company makes a network traffic analysis product. And one thing I've learned when we've been developing this and emulating various types of malware and various types of activities and whatnot is Go is a really great language for writing bad things. If you ever run a honeypot, you'll find a lot of Go in there nowadays. So Twitter, GitHub, so on and so forth. I'm not affiliated with Google. Go is a Google product, a Google project, I guess. I have no affiliation with Google. My company would like me to point out that the views in this talk are not theirs. Also, I'd like to point out myself that if you write malware and use it, or even if you write malware and put it on the internet, somebody might use it. So like, as cool as it's like, hey, I wrote this really cool thing. I think I'm going to send it through Canada. That would be awesome. Please don't do that. And when you do it, I'm Justin Trudeau. Pleased to meet you.
My name is Carson Cease. I'm a current student at the Pennsylvania College of Technology. This past summer, I interned with, thanks guys, classmates. I interned with Stuart at IronNet and a couple of other folks there. Did a little bit of Go development, which kind of sort of led to this talk. There's my equally legitimate Twitter QR code, if you're interested in that sort of thing. My GitHub as well. I'm also not affiliated with Google. And in addition to my past employers, my school does not necessarily endorse what we're going to talk about today. So speaking of talk, what are we talking about? First of all, just a quick overview of Go, kind of why it's good, why it's maybe not so good. Little Hello World demo, and finally, some malware bits.
Notes.
Real quick, some notes that you might want to follow along with, or you can see that link at the end of the talk. It has pretty much everything we're going to talk about linkified, so to speak. So Go. It's general purpose, curly braces, developed by Google. It's boring, which is nice. And at first, that term seems a little bit unusual. But let me put it this way. So you spend some time, a couple of hours, writing Lisp. And man, you just feel great. You get all of this code done. You spend like 3 hours on it, and you're just fired up. You feel like you're the best programmer ever. You just process some strings, and you feel great about it. Well, with Go, you spend some hours, and your code's pretty good. You're happy with it. But when you step back and take a look, you realize, hold on, wait a minute. I just wrote a worm that can actually take over the internet. Stu might know a thing or two about that.
Mr. Trudeau.
Right. So Go's compiled. It doesn't require anything, to be on the target, like a Java virtual machine or something with Python, some sort of interpreter. It's compiled, makes a binary. It's good for a couple of things, network clients and servers, and kind of systems level programming. What's interesting about those three parts is those all kind of, when you put them all together, it kind of makes malware, which is what led to this talk. So why malware? Why Go? 2 parts. It's easy and it works. It's easy. It has a large standard library. There's pretty much everything you need in that standard library when you want to get started. However, if you can't find something there, you might have better luck finding something in a library somebody else made, or make your own and put it on GitHub. You can't really get fancy, and that kind of goes back to the nicely boring. The code's easy to read if you're reading somebody else's code, and more importantly, it's easy to write. And kind of talking about easy, easy means fast. Fast means cheap code to write. And that means that when your malware eventually gets caught, instead of going through tons of time to make the malware really difficult to catch, really hard to interpret, you can just keep writing more malware. On the note of fast, it takes a weekend to learn. Just a quick side story about that. This time last year, I think it was in this very room I was sitting. There was a talk Stu was giving about some Go and some other bits and pieces there. And I thought, that Go seems pretty interesting. I had heard of it before, but never really followed it. But when I heard it could be used for malware, and I'm a cybersecurity student, I thought, I'll check it out. Went back to school, took a weekend, learned Go. And then the following summer, I was writing some Go for IronNet. So that's the easy bits. And it works. And when it works nearly everywhere. You can cross-compile to a bunch of different architectures. And when I say that, that means when you have a Linux toaster and it's running some obscure distribution, Go will probably run on it. And if your toaster doesn't have all of the dependencies you need to run Go, that's OK, because it builds them all into the binary. So you don't have to worry about any dependencies on your toaster that you're trying to do something with. Finally, it plays nice with C. OK, so that sounds like all kind of rosy things for working with malware. But what's the catch? What's important here? And what can be a drawback? They're really big binaries. If your toaster only has 4 megabytes of storage on there, you can't really fit such a big binary in such a small space. It's kind of POSIX focused in that it works well on Windows, pretty OK. That's really the only reason Stu can write Windows code. However, you're going to have a tough time writing Mimikatz. It's mostly cross-platform. There are some catches to that. It might not work on all toasters, but for the most part, it works pretty well cross-platform. There's some different like WebAssembly kind of things that Go can do, but not everything's quite there. And finally, dependency management is still a little bit young in Go, and it's in active development. There's also one other catch. All right, so we kind of know what the catches are, what's nice, what's not so nice. So what do you need to get started? First of all, you're obviously going to need the Go compiler. It's not terribly big or complicated. Download it from their website, extract it, set a couple of environment variables, and you're pretty much good to go. And if you're not so interested in downloading a big binary compiler to actually work with it, you just want to kind of play around, Go has a great website, play.golang.org, where you can run a little bit of everything, not quite everything. And it's a good way to just kind of learn Go, experiment. Go's nice because it doesn't require any crazy IDE or anything complicated to use. You just need a text editor. You could use Ed if you're into that sort of thing. If you're less into that sort of thing, Vim's not a bad option. Vim has a nice plugin for Go. And then if you're really soft, and I admit to this, you could use VS Code. VS Code also has a nice Go plugin. Finally, if you want to use some external libraries that other people created, Git's helpful to have.
Hi, so I've gone to a lot of these like, hey, use this thing, it's awesome talks. And they're like, hey, here's like why you should use it, it's really cool. And then you're like, oh, that's nice. And then all of a sudden it's like, and bam, we've just got on target. And you're like, whoa, 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 how did we get there? So we're just going to take a couple seconds and do a like how to compile a thing. It's real simple. You write your code in Vim, which is OK nowadays. We don't shame people for this anymore. You write your code in whatever text editor you'd like. And we all tend to use the same formatting style. It's actually like everybody does. Go imports will take care of that for you. So you write your code, you're like, indentation. And then you find yourself nicely indented. We'll see that in a couple minutes. After that, Go has this sort of like a linter-ish thing. It's a little like linter plus built in. So it'll check and see if you have unused variables or strange return values or whatnot. GoVet does that. We'll see it somewhere. We'll see it in a demo later in the talk. And then you just build and run it. It's a binary. You build it, run it, you put on target, run it, something along those lines. So here's a quick little demo of what it looks like. So we'll program in cat because apparently Ed is not cool anymore. So we'll write in cat, and you can see this is not perhaps the way you would like your code to look. But that's OK. So Go imports will handle a few things for us. It handles the package statements of main, just like your most languages nowadays. Handles your imports, what libraries you can use. So they figured out we're going to import something from the format package. And it makes it nice to look at. We'll vet it. OK, clean bill of health. That's cool. Compile it. We'll see that it is, in fact, an LSB, an ELF binary. It's nicely statically linked, which is quite good. It has a build ID in there. So that might make things trackable, but it's OK. We'll just put it on target and run it. And sure enough, we have our hello world. So really easy to do. It's also nicely injectable, both as a DLL on Windows, it works quite well. We'll see it on Linux here. But it's pretty much the same thing. Go has this concept of build modes. So you can build it as a binary. You can build it as a Go archive, like a C archive-ish. And we'll inject it however you normally inject things. So quick demo there. By the way, if anybody can tell me how to get rid of this black bar, it's like 6 conferences in a row now. I've been trying to figure out how to get rid of this thing. I'll buy you a beer. Did not turn it off and on again. No. Peanut gallery. All right, so here we go. We have a little program. It'll take and write a file tempx with a little hello from a PID message. There we go. Run Go imports. It's nicely formatted. Notice we have main here that does nothing. Just like in C, where you have attribute constructor, in Go, because we're going to make this a library, we have init, which is a constructor function, so it'll run before the main function or before whatever function is exported. It's good for malware. You just inject it, and then you have a thread going. And you're like, hey, cool. Got a callback. So here's Go vet in action. Up here is hello from PID, and I got a formatting directive, but I didn't put anything in there. And sprintf works like sprintf in C, hopefully using something better than sprintf. But yeah, so we need a %v, which is just any verb at the end. We'll go change that real quick. Find the line where we goofed. It was line 11, it told us, and we'll add a get PID in there to print the PID. So there you go. Go imports gives us a clean bill of health, nicely formatted, so on and so forth. We got our little import line taking care of us nicely, which means you don't have like a billion includes like you have in C, where you're like, do I really need all these? Is that debugging? So compiles nicely. Turns out it's a shared object, but heads up, it's dynamically linked. You can statically link shared objects. It gets a little wonky, so especially if you're cross-compiling them. Put it on target, shove it in. Notice we got a bunch of threads now. And that's pretty typical. The Go runtime, it's not an interpreted language by any means, but it's garbage collected. So you do actually have a runtime there. And then we got the thread started, and then we get DL open mode returning. So racy-ish, but it's threading for you. It's kind of normal. And yeah, we got our hello. So there you go.
So the first little bit of malware we're going to talk about is domain generation algorithms, or DGA. And sort of the high-level overview of this idea is you have a defender, and you have your malware inside his network. And your defender, blocking a couple IPs, a couple of domains, a couple thousand IPs, a couple thousand domains, how does your malware reach out? So one way of doing this is creating sort of predictable domains that the malware reaches out to. And then you, the attacker, will register a handful of those that the malware can eventually connect to. It can still be blocked, and there's different ways of doing that. But for the most part, it's a little bit harder to get around since it's just random. However, it's not totally random. Under the hood, what you're doing is you're using something like the current day, which might involve the year, the month, the day, some combination. You might have a seed. You might have an additional string in there. And you, the malware author, it's predictable to you. You know what to expect. The defenders don't necessarily know what to expect. It's pretty easy to implement, and it's hard to detect. But what does it look like? So here's some of our domains. All right, we use our DGA algorithm to generate a handful of domains, a couple for Monday, Tuesday, Wednesday. And our malware, he's going to try every single one. Doesn't know which one's registered, which one's not, but he's going to try them all. And we're going to register 2 of them, one on Tuesday, one on Wednesday. So when our malware reaches out on Tuesday, it gets in touch with that domain, and same for Wednesday. Our poor defender, though, he doesn't know what to block. He sees all of this getting reached out to, and he can block some things, but he can't block a 7-letter string for popular video site, YouTube. So it's not exactly easy to get around, and it's easy to implement. So what's going on here under the hood? First, we have in this case, our string of our year, month, day, and then some sort of counter to make it change for all the domains you want to generate every day. We hash that, in this case, MD5. And then we use that, we append our top-level domain, so our .com. We append that to that string, and then we return it. I actually wrote a DGA library in Go, both sort of for the purpose of this talk to show how easy Go is, and also to kind of put this together and say, hey, look, we can get a time. We can create a new domain generator using the year, month, the day. We give it our top-level domain. And then we just call generator.next every time we want a new domain. And we can use this on the malware side that's implanted somewhere. And then we can use this on the other end to create a whole list of domains and pick the ones we want to register. All right.
I will help you.
So what does this look like? Just a quick bit of code, already formatted. We have the domain generation library that I wrote, rsdga, imported. We're just grabbing the current time. We're creating a new generator. And that generator is using current year, month, day, com. The thing here is the way the library is written could be com or .com. And of course, this isn't exactly what you do in real malware. But just to give an example, we're just going to have a for loop run 5 times and print out 5 domains. So we run our go imports, looks good. We run our go vet, looks good. We build it, and we run it, and there's our 5 domains.
Cool. So it's a great way to establish your C2. Now you've got comms, usually HTTP. Sometimes HTTP is not quite what you need. Either it's heavily scrutinized. Maybe they do some TLS man in the middling or something. You're like, it's not a great way to go. So another easy thing, either easy way to get data off of a network is DNS. You can always trust HTTP, HTTPS, and DNS to get out of a network. DNS is often a little less scrutinized. It's like, I don't know, it's like control plane stuff. I'm not going to watch that too much. Or, hey, we've encrypted all our DNS. We can't see it, but we encrypted it, so it's cool. Easy way to just say take a bit of data, not too much perhaps, is just chunk it, encode it, encrypt it, and stick it in a DNS label. If you run the DNS server, you'll get that query because if you're doing it right, it's going to be a never-before-seen query. A couple caveats here. A DNS packet usually is it's supposed to be under half a kilobyte-ish. Usually you get like 100 bytes-ish, if that. It's actually kind of a big packet, so it's not fast. Also, it's case insensitive, so if you're playing with this, expect cases to change in your queries as they go from implant to server. And it's kind of one of the cool things that's used nowadays. So that's what it looks like graphically. We have our implanted victim machine, and it says, hey, on the network, it says it's internal DNS server, probably it's DC. Hey, I'd like this ridiculously long thing, please. And the DC is like, I don't know, ask this guy. And this guy's like, I don't know, ask this guy, the upstream DNS, so your info blocks or 8888 or something. And typical normal DNS recursion goes on. And at some point, you own boringcdn.com, oh bad guy. And you get this long query, and you're like, I'll just decrypt that. And now I have a bit of exfil. So a little more concrete example. Grep out a roots hash from Etsy Shadow. This is made up from a dummy account, by the way. See people like on their phone. There's base 32 encoded. Base 32 is like base 64-ish. There's 1 fewer bit per byte you get, but it also is case insensitive. So it doesn't, case changes on the wire won't affect it. And servers do change case. So we'll take this nice encrypted large thing, and we'll just chunk it into bite-sized chunks, put it in a query. By the way, it's good to have a bit of randomness so that no caching happens, so you get everything to your server. Speaking from experience. And then we'll exfil it. So this example, we'll just say we've done some host survey. We've run a netstat, and we've enumerated the drives, and we've looked at the process listing and whatever else, chunk that, stick that in some variables, just a blob of bytes. We'll trunk the bytes. And these typically are not just a function call, but we'll chunk it into some bits, and then each chunk will exfil it. So we'll take, make sure the chunk is, thank you, Google. That was helpful. Make sure our chunk is small enough, and we'll just, damn it. We'll just call just look it up as an IP address, like you'd look up any other IP address, except we'll hex encode it, stick it on our domain, example.com, boringcdn, whatever. Just register it and point your name server records. And probably we'll do some sort of encryption with it. Encryption's nice, by the way. It adds entropy, so it won't get cached. It actually doesn't make that great a demo, so I didn't record one, so apologies.
However, that said, Go Playground, not really a demo. This link you can see in the notes that will be linked at the end, but also in the slide deck. Not a great demo, but it does kind of show what's going on here as far as, hey, you can hit play on Go Playground, and you can see here's your input, and here's the output, and then here's how it decodes it. So just something worth mentioning.
Yeah, it's also a nice library Carson's put together to do exfil over Go and take care of some of the boring bits. Next thing to talk about that Go makes particularly easy is domain fronting. Domain fronting was kind of a hot topic a few months ago, maybe a year or so ago. And really under the hood is it's just you have your TLS connection that says, hey, server, I want to make a connection to this thing. And it's just like an encrypted tunnel, basically. And then you have the HTTP under the hood, and HTTPS is just HTTP wrapped in TLS. That's all it really is. And HTTP already has this like, hey, I want to talk to this thing. So you have two sets of, hey, I want this. And normally they're the same. And sometimes they're not. And if they're not on the wire, all you can see, unless you do TLS man in the middling, on the wire, all you see is the outside, the TLS SNI, the server name indication. So, hey, I want to talk to YouTube. And then it hits whatever provider, and the provider's like, oh, I have this HTTP request. I know how to route this. Awesome. And they don't really always check. The major providers, Google, I think Amazon now, they've made this hard or impossible. But some of the smaller ones, it works pretty good. And it's really quite hard to find on the wire unless you're doing some really cool endpoint stuff, which works. It's pretty easy to implement. If TLS man in the middle happens, oftentimes those two streams are not reassembled. There's no correlation between the TLS and the plaintext. And it's pretty much every tool nowadays supports it because it's just simple. This is what it looks like graphically. You got some implanted victim box, and he says, hey, I'm going to make this. Thanks. Go away. It's going to work. We see now. I can't see that. He's going to say, hey, I'm going to make this TLS request to kittens.boringcdn.xyz. It's normal. Under the hood, he's going to be, hey, I want bad guy, the bad guy.boringcdn.xyz. And the firewall's like, yeah, cool. Kittens are nice. I like kittens. I was told to watch out for this bad guy thing, but yeah, it's not there. I can only see the TLS. And the web server that serves all of the CDN, and CDNs do this pretty well. It's like, yeah, sure, here's the cert going this way for kittens, and I'll route it to bad guy going this way. So we have our nice C2 that uses whatever we've set up on the back end. But on the wire, it's just kind of cool. There's a couple ways you can do it in Go. So one way is like this. You make your nice HTTP client struct, and you make your HTTP client, and you just say, hey, for anything when we connect TLS, make the SNI something benign looking. And then, when we do our GET request, get something sneaky, but on the wire, because you set the TLS config, it'll do that. And, you get your response and do whatever you do with your response. Thank you. That's cool. We'll just print it out. You can totally pipe it to a shell or whatever. Another way to do it is like this. Quick detour, one of the cool things about Go is you can change variables at compile time. So it's really good for an implant ID or I know there's this particular thing in this box, so just declare them globally. So the SNI will keep as this benign domain fronting demo thing, .ga, and we'll play with the host header in a bit. There you go. So we'll just, the other way to do it, you roll a request, just like you say, hey, I would like to make this HTTP request, but you set the host here. And you set the host to something that is not the SNI. So in this case, by default, it'll be dfdemo.ga. And then, we'll just make an HTTP response. And this is as easy as it is, actually. And we'll just, in this case, we'll print it to standard out. We could totally have piped it to a shell when we run it. So running it looks like this. Clean bill of health, good. And sure, our SNI is dfdemo.ga. Our host header is dfdemo.ga. And it was not found because can we go back? Damn it. The request for tasking, hey, the domain fronting demo is not going to give us any sort of tasking. If, however, we set that host header at compile time to something like a badmoose.ga, something that is going to give us tasking, compile it, run it, there we go. It's like, oh, hey, that's kind of cool. And you totally could just pipe this to a shell. Linux Lady did something like that. It's just like curl piped to sh and cron, and it actually works pretty good. So that is domain fronting in Go. It's really quite easy. It fits in a tweet, I found out, and good luck catching it. So unless you do TLS decrypt, TLS man in the middle, and it works okay sometimes. Last thing we'll talk about, propagation via SSH. So an SSH worm. These have been around since Mr. Morris got himself in trouble, or I was telling it or something, but these have been around quite a long time. It's the same SSH we use all the time. It's the same, even Windows is getting SSH nowadays-ish, kind of. Really what they did was they just took Linux and put it on Windows, like, hey, we have SSH now. So what this one will do is it'll just try a set username and password everywhere. And then, I always get, yeah, but in our environment, you can't do that because everything has a unique password. And you're like, you sure about that, buddy? So just out of curiosity, how many of us have seen somewhere maybe cred reuse like crazy? There's like a lot of people who are like, kind of. What's your company name? Also, password auth is pretty common. It's actually watching a honeypot once. It was like, man, everything is trying passwords. They're not trying any other authentication mechanism that SSH supports. So here's what we'll do. We will take a TCP port, and we'll just listen on it. It's kind of a mutex, kind of like a, hey, we only want to implant once. One of the reasons that Morris got in trouble with his worm is he kind of brought the little nascent internet to his knees. And there's no like, okay, that's enough. So when this thing implants a box, first thing it'll do is try and listen, and if it can't listen, it'll die. And then it'll just take this creds pair that we've built in, and it'll try it everywhere it can. I've written this one to only go after 10 whack 8. Turns out if you put a worm on the internet, people will use it. And then it turns out people notice that people use it and ask you about it. So don't do that. So yeah, and if it all succeeds, it'll take, it's Linux specific. So Carson mentioned like, hey, sometimes it's not totally cross-platform. Well, we'll go even worse and we'll just read from proxself.exe, which does not exist, not on Linux, but that's okay. We'll copy the worm, we'll start it to the next box, we'll just drop a binary, and then we'll iterate. There we go. So you can make nice command line arguments, and if your software is meant to be used by users, it's a nice thing to use the flag package to build command line arguments. The other way to do that is just to have this massive var block at the top and say, hey, this is the config, and do compile time config if you want to change it. So, simple things: set the creds, the first octet of all the hosts we're going to go after, so on and so forth. Set the binary names. Interesting little thing that we won't see in this demo, or won't see in the slides. I don't have a demo for this one, but I was like, hey, cool. So I have this network of 100 VMs set up, which is really good for your processor's heat, by the way. I have 100 VMs set up, and I was like, I wonder if it's done. It's like, oh yeah, I should have it talk to me. So it'll just make a query to kittens.com. I could not find a good way to record a demo other than watching DNS queries come back and they're all for kittens. Okay, that's kind of boring. So we'll just look at chunks of the code. If you would like, it's on Git. It's I think a GitHub gist. I put it in there. So the mutex, the preventing multiple executions. Listening in C is great. You ask for a socket, then you bind to an address, then you call listen, then you call accept, then you maybe do a bunch of ioctls and all sorts of great stuff here. Listening on Go is sort of a one-liner. And this is like a Go one-liner. Go is a very vertically long language, but it's a Go-ish one-liner-ish. But anyways, if it fails, then we're like, oh, probably couldn't listen on that, and life goes on. Making an SSH connection is you just make a config and you tell it to connect. It's almost like command line SSH, except in code. So you just give it a username, like a list of authentication methods. It actually lets you validate the host keys, which is really nice. Some sort of connect timeout, and it's thanks. Yeah, we should have gone with the PDF. Yeah, we totally should have. When we were giving the talk, we were like, hey, PDF or Google Slides? Whoops. So yeah, and that. By the way, if you replace ssh.dial with net.dial, that's how you make a TCP connection. So it's Go is a pretty regular, boring language. And then we'll propagate. So we'll take, you have your SSH connection. We'll call it C. Thank you. SSH is a multiplexing protocol. SSH really, if you boil it down to it, it's just a tunneling protocol, and it makes channels inside of it. So we'll make a session channel, and we'll connect standard into that channel to the worm. We'll have read the worm in from proxself.exe. And then we'll just say, hey, in this session, run this really massive command, and we'll that payload bin from 3 slides befor, where it's like, yeah, we'll call it cron d, because nobody's going to kill cron d, right? So we'll write to cron d in temp, because cron d always runs out of temp. You'd be surprised, actually this works. Oh, hey, don't read ahead. Sneaky. Yeah, totally should have used a PDF. And going back to the whole easy thing, that combined output thing, you replace session with os.binsh or something, or os.command.binsh, I forget what it is. That's how you run a command. So it's, the theme and variation is kind of it. It's really not the most exciting language to write, but then you do awesome things with it. So that's in a nutshell some cool things you can do with Go. If you stitch them together, you have some pretty cool malware there. There's all sorts of stuff. There's a lot of frameworks out there that use Go under the hood. Few things I found from experience. It's much easier to write if you have some sort of editor plugin. It doesn't particularly matter what editor you use, because you're going to format it the same anyways. If you're using Vim, there's Vim Go. If you're using VS Code, some people use VS Code. Microsoft has a library out there, or a plugin out there. Carson mentioned both the tour and the playground before. The tour is really nice. It's like when people are like, man, how do you program? I'm like, here, take this tour. And 2 days later, they're programming. We don't have a REPL in Go. It's a compiled language. It compiles really fast. I've not seen anything take more than a couple minutes. But the playground is pretty close to that. And actually, a lot of the plugins, at least on good editors, we'll just send things to the playground if you ask. So a couple more things. Trim path, when you pass it to the Go environment, or when you pass it to the Go compiler, will trim the path of files out up to some namespacey thing. So if you just have something sitting in your home directory, a single file, and build it, you won't put your home directory in it. My boss at one point, old job, was kind of giggling. I was like, okay, you're a grown man, why are you giggling? And he's like, hey, this is your malware, isn't it? It's like, yeah. It's like, well, I strings it and I found your name. I'm like, yeah. He's like, there's an incident spun up because of this. Apparently, if you leave things for months on a domain controller, people notice. But they don't notice like strings it and find my name. Good stuff. And then last thing, if you use cgo enabled equals 0, it's an environment variable you can pass to the compiler. Dynamic linking won't happen. Every so often, the static thing is, it's like, hey, in this one environment, we're going to use this box's DNS or something. So usually if you're writing malware, you want to do that as little as possible. So that's the bulk of the talk. We're going to open it up for questions. Before we do, from giving this talk in smaller and larger and so on environments, I've learned a couple things that are better for Twitter or meeting us in the hall or IRC or something along the lines. So asking how to, just like, hey, how do you get started the tour? That answers that. And then invariably somebody's like, hey, I tried Go and I hated it because I had a bug, question mark. So whenever you talk about Go, also if you use OpenBSD and you ever get to talk about that, you'll get this too. Somebody always says something to the tune of, hey, my thing uses this language or design choice or editor, except maybe VS Code, or paradigm, or this is the best Power Ranger. Question mark. So yes, I agree. I'm happy to talk with you in the hall. So I'd like to open it up to questions. There's QR codes. There's those notes again. And then if you really don't like QR codes from a pair of hackers, there's our Twitter usernames. I think that's the first time I've ever put this slide up that somebody is like taking a picture of me. So yes. So the question is, if Go is statically built by default, build static binaries by default, why would you think about this? And the answer is, it's almost always statically built by default. But the one I remember is on Linux. If you're building on a Linux box and deploying to a Linux box, I think, if I recall correctly, it'll call get host by name or get address info, I think, and not just make a UDP socket and roll its own packets. Roll its own UDP, a few things like that here and there. And that might be cool, and maybe you don't want that. So I find it's a little easier, then I don't have to worry. Because libc, or glibc likes to change get address info, like subtly. Any other questions? Yes?
How much is antivirus onto Go link?
So I'd say most of the time when we go to a client site, my company does network stuff, right? So mostly we're worried about what network defenses are going to catch us. And we tell them, hey, dudes, like, feel free to disable your AV or whatever. And they kind of like snicker at us. They're like, yeah, OK, buddy, we're going to disable AV with some random stuff on our computer. And then we should just put our stuff in GitHub. And we pull it down from GitHub, and it works. And we're like, hey, by the way, this is malware. And oh, no, that's not malware because you wrote it. And it's like, we got a shell. So that's my experience. If I forgot to repeat the question, I'm sorry. The question was, how much does AV catch this kind of stuff? And generally, if you roll your own, whatever language, if you roll on your own, nobody's going to notice. So.
Does using Go present any real challenge to reversers?
So I've asked a couple, and the question was, does using Go present any real challenge to reversers? And I'm not one, so I can't really speak hugely definitively on that. Like Carson was like, yeah, and then they catch your stuff, just write more. I'm on the just write more side of it. But I've asked that to a couple dudes, and I've got a couple different answers. One guy was like, oh man, I hate it when I get Go because it's such a weird format and all the strings are funny. Then another dude was like, dude, I love Go. They have debugging information everywhere. So I don't know. Any other questions? Yes?
Have you ever seen sophisticated malware in Go?
No. Question was, have I ever seen sophisticated malware in Go? And the answer is, I've not. There's some open source frameworks that are pretty slick out there. The malware that, again, not being on the defensive reversey side of it, I don't see a lot of malware. But there's no reason you wouldn't catch it. But if it's actually really sophisticated, probably not getting caught. So there's no reason you couldn't write it, for sure. The things that I've just fiddling around with honeypots are, not great, but haven't reversed them. So sorry, red teamer in the back there.
Since Go builds its own or brings its own libraries with it, have you run into any instances where the size of the payload brings along its own restrictions as far as payload delivery?
So the question was, since Go brings everything and builds a massive binary, have I run into any issues with binary size being a problem? Paraphrase. Yeah, I've not been in that situation, no. I've not yet found a toaster to implant. But back when I was fiddling with routers, Soho routers, it would have been a problem if I were putting Go things on there. Some of them really only have a couple meg of memory to fiddle with. And memory and RAM disk-ish, yes?
How large are your typical binaries?
Like 4 or 5 meg, 6 meg. If you put a lot of cool stuff in there, 7, 8, 10 meg. If like the worm, if you're building another binary into your binary, they get 6 meg plus 6 meg, and yeah, so they actually get kind of sizable. So, but nowadays, I mean, it's not that usually big an issue. Yeah. So, any other questions? All right. Well, thank you for coming to our talk. Hopefully, it's useful for you. So,